Yes, okay. Okay.
So it's my pleasure to introduce the first speaker of the afternoon, Peter Scholze of Bonn, and as I very, very recently found out, he's telling us about the pro-étale setting.
Well, yeah, thank you, and thanks for the introduction. So, yeah, so I want to talk about my joint paper with Bhargav Bhatt. About the pro-étale side, because I've never done that before. So, so say let's fix an algebraically closed field of some characteristic, and some prime different from the characteristic, and so what I want to talk about today are some purely formal comments. So. On what these étale cohomology groups of X with ell-adic coefficients actually are. So what's the point? So the problem we might have is that those are not étale cohomology in the usual sense, so as sheaf cohomology of the usual sheaf QL bar. I mean, if you want to be less fancy, you can also just put ZL here. But anyway, so namely, if you would take the usual sheaf cohomology of QL bar, then those would satisfy that's the étale cohomology, or maybe let's put the étale really here so that we're really talking about cohomology of this étale side, the square bar coefficients. This would simply be the cohomology of Q tensor up to QL bar, and it's well known that those guys are not well behaved. So, of course, it's well known what the correct definition is. So, you simply formally define them as taking what you get for torsion coefficients and then, first of all, taking the inverse limit over all n and then tensoring this up to QL bar. And I mean, that's a perfectly workable definition. But so there might be some problems you might have with this definition. So let's see what I wanted to say. So the first thing you observe is that this definition is only reasonable if you already know that these cohomology groups are finite, which of course is a theorem in this case, so there's not a problem here, but more generally there might be. So only reasonable because these guys at finite level are finite. And so they automatically satisfy some Mittag-Leffler condition. So in general, we should also incorporate some lim1 term. So take and I mean, you can do this, and Janssen gave a formalism to do this. It's called Janssen's continuous cohomology. So for example, if you take some x, which is defined over the rational numbers, and take the cohomology already over the base field, then you should apply this formalism. Something else you can observe is that if X was some usual topological space, then you would really have some, not just some groups, but really some complex. And actually this complex comes with some additional structure. It's actually a commutative differential graded algebra. And it's far from obvious that there is a commutative DGA, which one might call R gamma etale XQL bar, with those cohomology groups. This was done by Deline in his WL2 paper, the construction of such a DGA. But it's actually quite subtle. And there is a recent paper of Martin Olsen where he wanted to use this commutative DGA structure in some relative setup, and he really had to use some very roundabout way of proceeding in that situation. And a third problem you might have with this definition is that actually in this definition it does not define what QL bar itself is. It only defines what its cohomology is. And this is bad in a relative setup. So if you have some map f from x to y, then you would like to know what RF Lowersdorff QL bar is in general. And if you just think about the case where f is the identity from x to x, then particularly would like to know what QL bar itself is. And again, this can be repaired, so there exists some constructible derived category of QL bar sheaves on X as defined by Ekedal. Or really, Ekedal is only working with ZL coefficients, but maybe the remaining steps are not so difficult. But in any case, the definition is extremely subtle and technical. And so what I want to talk about today is a formalism where all of these problems are taken care of in a uniform way. And so first I want to talk about where these problems actually come from in some intuitive way. Or really, why doesn't it make sense to just talk about the cohomology of QL bar in the naive way? So let's look at the following example. Let's take E over K in some elliptic curve. Then it's well known that its first etale cohomology group, just with C mod L to the n coefficients, or in this case I want to put it here, is related to the Z mod L to the n squared cover given by multiplication by L to the n on E. So it's due parameterized homomorphisms from phi 1 into L to the nz. And so this indicates that really this ZL cohomology group should be related to this inverse limit over multiplication by L on E projecting down to E. And now this looks like some horrible object, and certainly it's not a finite type, but it really exists as a scheme. So because all the transition maps are affine, and they're even finite. So it's a bona fide scheme. And so somehow all we have to do is to allow such huge covers of the space in our formalism. So, so this is supposed to motivate the notion of pro-étale maps. And, well, I will always use the word pro on schemes, and if I work on the level of rings, I will call them int because certainly it's contravariant. So a map A to B of commutative rings is ell-adic. It's meant to be self-explanatory. So if B is a direct limit of étale A algebras EI, and this direct limit here is filtered. Again, there is a small problem which you might have with this definition, namely it's not really a geometric notion. So so you can have a morphism which is Zariski locally ell-adic but is not globally ell-adic. So into B. Which are Zariski locally on A. Or spec A. Ell-adic but not themselves. So there is an example by de Jong of such a map. And so this motivated us to look for a more geometric notion to use. And there is such a notion. That's what we call weakly étale. Previous in the literature, it was also called sometimes bi-flat or absolutely flat. If both the map itself and the multiplication map are flat. So if you think geometrically, so if Y to X is a map of schemes, this weakly étale if f and the diagonal from y into the relative fiber product of that. So that's obviously a geometric notion because flatness is preserved under, flatness is an FPQC local property. But a priori you might think that this is some kind of very general notion. And so let me already at this point give the following exercise. So if A is some field, then show any weakly étale K algebra is already int étale. So if anything is flat over a field, a weakly étale simply means that the multiplication morphism is flat. And so, yeah. In this case, it's somehow not too big, this algebra. I don't think so. I think if you take a transcendental extension of your field K and take its tensor product, so some basic proposition is the following list of implications. So étale certainly implies int étale, which in turn implies weakly étale. So why is this? Certainly an étale map is flat, and the diagonal is open. Open maps are also flat. So any étale map will be weakly étale, certainly. But flatness is preserved in the filtered colimits. So anything which is int étale also has to be weakly étale. Then one can show that this implies that the cotangent complex vanishes. And this implies, by deformation theory, that the morphism is formally étale. So in particular, étale is equivalent to this flatness property of being weakly étale plus finitely presented. So weakly étale is some kind of étaleness without the finite presentation assumption. Okay, but so it's clear that int-étale morphisms are somehow tightly related to étale morphisms. They were very close to them, but weakly étale morphisms a priori might be very wild. And so a theorem we have to prove is that in fact the class of weakly étale morphisms is in some sense controlled by the int-étale morphisms, and that's the following theorem. Let A to B be any weakly étale map. Then there exists some spacefully flat int étale map from B to C. such that the composite is int-etale. Or in other words, up to some pro-etale localization, anything which is weakly etale becomes pro-etale. Okay, and so this makes the following definition reasonable. So let X be a scheme and then I call this a pro-etale site, but it's really made of these weakly etale schemes. But because of the theorem, there's not much of a difference. So those are the weakly etale X schemes, and covers, he makes this into a site by declaring covers to be those which are covers on the FPQC side. Thus, objects are locally of the form some spec B mapping to spec A sitting inside of X, where A to B is int-etale. Okay. Let me give an example. Let K be an algebraically closed field. And then X pro-etale is equivalent to the category of local profinite sets. Where sending any y to its k-value points, which is also the underlying topological space. And covers are described in the following way. If X is a profinite, so if Y is a profinite set, and the FIs are maps, where again these are profinite. Because everything is locally profinite, you easily reduce the description of covers to this case. Then they form a cover if and only if they are jointly surjective. So in particular, even if X is nice, the objects in this pro-étale site, they are usually not connected, not even locally. Instead, you have a locally profinite set phi naught of y of connected components. So the connected components are naturally organized in some locally profinite set. But this makes the following definition reasonable. So let T be any topological space. And I'm particularly interested in the case where T is totally disconnected. Then with it, you can associate a sheaf, let's call it f of t, on the pro-étale side by saying that on any y, it's just a continuous maps from the underlying topological space of y to t, or also from its connected components to t. And now this really sees some topology of T. And so by regarding QL bar as a topological space, we get a sheaf QL bar on the pro-étale side, which sees the topology of QL bar. So if this T was a discrete space, then those would really be constant sheaves, but there are really some kind of enhanced versions of constant sheaves. Makes sense? And so the basic observation is now that this sheaf now actually computes étale cohomology with QL bar coefficients. So if X as before and L is not a characteristic, then this thing as defined by Grothendieck is really canonically isomorphic to naive sheaf cohomology of this sheaf on this pro-étale side. So let's see how this addresses the issues that I had with the original definition. So first of all, the right-hand side is always reasonable. So in particular, you get back Janssen's continuous étale cohomology. In more general setups. Secondly, it now really makes sense to talk about the derived functor of global sections on the side. So this will certainly give you a complex, but actually by general nonsense, this will produce a commutative EGA. So you get this for free. And the third point is that now we really defined QL bar itself. So So you mean the class of maps which are in some sense, so yeah, a map is weakly étale if and only if it's FPQC locally int étale. Or in that case, it's even pro-étale locally int étale. And because, I mean, if this is int étale, then certainly the flatness properties are true, but then you can descend those flatness properties along this faithfully flat map.
And what if you just look at that definition of a weakly étale map?
Hmm?
If you just look at that definition of a weakly étale map?
Then it's not so easy to compare this to étale cohomology. Because you have to relate general covers by weakly étale maps eventually to covers by something étale, at least for for cohomology with torsion coefficients. And for those, you need to split them up into something étale. I mean, you might also try to just redo all arguments in SGA starting from weakly étale maps, but I don't think it will work. So I think you really need this. And it's still nice to reduce to something of finite type eventually. And so I said that ell-adic has this rather complicated definition of this bounded derived category of constructible sheaves. But in fact, that's something very simple now. So we write this down. So those are all those complexes of QL bar sheaves. So QL bar here denotes X pro-étale, and QL bar denotes this sheaf. So you can consider complexes of QL bar modules. And certainly K should be bounded. And also, it should be constructible. So this means that there exists some stratification xi to x such that all cohomology sheaves of the restriction of K to the stratum are locally free of finite rank over this sheaf QL bar. And I guess I assumed that X has topological, that the topological space underlying X is Noetherian. If you make this assumption, then that's the correct definition. And I guess ell-adic made some much stronger assumptions about X. Yeah. So in general, this gives you a bona fide definition of this category. So, lots of time. Okay. Okay, so you can address these things. I should say that a priori there might be new issues that arise. So the main issue is that it's not so clear whether what we're computing there actually has a meaning, because we're taking some kind of covers by these weakly étale things, but they might be huge and get larger and larger, and maybe you pick up more and more cohomology classes as you take larger and larger coverings. And so we didn't build in any finiteness assumption, so it's not clear that we don't run into any problems here. So we need to control size of covers. And so the following definition is very useful. Let's call a ring A. Call this W contractible. So W stands for weakly. If any faithfully flat weakly étale, say, map from A to some B, so geometrically any cover of spec A in the pro-étale side has a section. So in other words, you can find non-trivial covers of this. Of spec A. And it's not clear that such guys exist. Well, it is clear that some exist. If A is strictly Henselian local ring, then it's W contractible. And a rough form, so we give a classification of these guys, and roughly it says the following. So A is W contractible. If and only if spec A is, and now I'm not being completely precise, so it's some kind of disjoint union, but of spec of some strictly Henselian local ring. Well, it's not exactly disjoint, but the set of connected components will be some extremely disconnected set. So the reason we don't call this contractible is that it's not assumed to be connected. But apart from that, all these connected components are contractible, and it's more or less a disjoint union of them, but not quite. So for this, we call the definition that a profinite set S is extremely disconnected. If for all surjections T to S, where this guy is again profinite, there exists a section. So it's some version of this where we just think about profinite sets. And for them, it's actually easy to give examples. So what's a good letter? T is any discrete set. Then the Stone-Čech compactification eta of S is such a guy, is extremely disconnected. Because if you have a surjection from something to it, then first of all you can lift this, you can lift this discrete set T in any set theoretic way, but then by the universal property of the Stone-Čech compactification, this extends uniquely to a section. Okay, and so the second part of this theorem is that any A admits a faithfully flat int-étale map A to B with B with B W contractible. And you should think of B as being roughly the disjoint union of all the strictly Henselian local rings of this A. But again, it's not really disjoint, there's some subtle gluing going on. And for this reason, this is actually not so easy to prove. So you can't just take the product of all the strict Henselizations, you really have to do something more subtle. So this means that yes, okay. So thus, if I start with a general, say, quasi-compact and quasi-separated scheme, I can find a simplicial cover x dot to x such that all xi are W contractible. So it's spectra of some W contractible rings. And this implies that I can compute cohomology on the pro-étale side of any sheaf F by applying F to this simplicial resolution by these W contractible guys, and then forming the associated chain complex. So, and so it actually is something well defined. So another observation that you can make is that so you can always resolve any scheme in the simplicial way by W contractible guys, and then you can look at the connected components. So any scheme X, you can associate a simplicial profinite set by naught of x dot. Of course, this depends on the simplicial resolution, but it's well defined up to simplicial homotopy. And because you can compute cohomology in terms of this simplicial guy, you can actually compute Q bar cohomology, etc., in terms of the simplicial profinite set. So this somehow refines Artin-Mazur's étale homotopy type. Which I recall is a pro-simplicial set. So there's someone looking at the inverse limit of all the possible ways of covering X by something étale. But in this way, we can actually somehow shift this pro inside and get some refined information. So I think you could essentially get this pro-simplicial set here by looking at the maps from the simplicial profinite set to simplicial sets, usual discrete sets, and then looking at the inverse system of such. Okay, and so what I want to finish with discussing also refinement of the usual étale fundamental group, which we call the pro-étale fundamental group. And we don't prove any finiteness. Yeah. Yeah, but we deduce this formally from the usual constructibility results for torsion coefficients. So we take what's known for torsion coefficients and then we have some formalism to lift this to statements now for ZL or QL bar coefficients. Yeah. I mean, we don't prove more than what was already known. Yeah, I don't know either. No, I mean, in the relative setup, yes, but then there's a Galois cohomology, and I don't remember what's known there, but the experts in the audience maybe. So recall from SGA1 that if X is any scheme, yes, I only need it's connected, and X bar is a geometric point, then one has the étale fundamental group, which classifies finite étale covers. So an example, you can look at P1 with 0 and infinity identified, so over some algebraically closed field. Then the étale fundamental group of X pointed at this node, say, is a profinite completion of Z. But actually, you observe that you can define something more refined in this case, because in this case you have the following. So this classifies the finite cover. But actually, in this case, you have an algebraic infinite cover, because you can simply look at an infinite chain of P1s and fold them all into this cusp. So this usually étale fundamental group would only classify those which become periodic after some stage, but really in this case, you have this purely algebraic infinite covering. And so what's a good definition of this? So what is an infinite cover? Well, you simply adapt the definition from topology into algebraic geometry. So I guess you would call it a cover if there exists some FQC cover x prime to x such that if you form the fiber product, then this will just be a disjoint union of the base. Okay. So in this case, you can pull back this cover along itself, and then you will see that it's just a disjoint union over the integers of the base. So this is pretty hard to check in practice. So you would like to have a more intrinsic definition of this. So you can observe that certainly this map from y prime to x prime is étale, and because étaleness can be checked FPQC locally, the original map has to be étale. So let's call this f prime. F prime is étale. Thus f itself has to be étale. And also, this is disjoint union of things which are proper. Well, they even the identity, but in particular they are proper. So this implies that f prime satisfies the valuative criterion of properness. And again, you can descend this, so you know that any such f has to satisfy the valuative criterion of properness. Yes. So you can pull back the cover along itself, and then it will be a disjoint union over the integers of the base. No. The problem is that then in that case, the union wouldn't be disjoint, but again along some components would form some profinite set. Okay, and what we prove is that those two properties actually characterize covers. So at least if x is not totally bad. So if x has locally a finite number of irreducible components, so for example, x is locally Euclidean. Then a map is a cover if and only if f is étale and satisfies the valuative criterion of properness. And in that case, one can actually choose this trivializing cover x prime. One can actually choose this to be pro-étale over x. And in fact, our proof uses these W contractible guys in a very non-trivial way. Okay, so in general, this FPQC cover x prime that you take, there will be some really strange thing. And so you can then define some topological group pi1 pro-étale. if the scheme is smooth, then the pro-étale fundamental group is the same thing as the étale fundamental group, or more generally, if it's normal. Yeah, so, I mean, also the fundamental group doesn't change. So. I mean, this business with the pro-étale fundamental group is really something about non-normal schemes. Yes. Yes. It's not classified by this group. So again, this is a topological group, and you consider the discrete sets on which this group acts. And in fact, it's not completely formal to get this group. So again, you have some kind of Talakian formalism, but it's not clear that there are any automorphisms of the fiber functor. So we need to produce elements of pi1 by hand. Right. And so how do we do this? Let's do this in the example of this curve. So we want some loop here. So we take this as our base point, and then somewhere here there's a generic point. And then specializations of geometric points. So there is one path from 0 to infinity, which is given by the valuation ring with this special and this generic point, and the valuation ring goes along this direction here. But then there is another valuation ring which goes along this branch. And so we can first go along this branch from 0 to the generic point, and then along this other branch from the generic point back to 0. And this gives us a loop in our scheme. And so you can generalize this to get enough loops in any such sort of scheme. Z. Sorry, I should have said that. Yeah. So. I should also say that in SGA3, they raise this point that in this case you don't get the correct thing, you should get Z. And they define some refined fundamental group, which in this case gives you Z. But in general, it's still not good enough. So the point is that you would like to know that QL bar local systems on your scheme correspond to continuous representations of this fundamental group. So that's satisfied if you have Z here. But if you have a higher genus curve and identify 2 points again, then it will be wrong in general for the SGA3 fundamental group. But with this pro-étale fundamental group, it's always true. So with this pro-étale fundamental group, QL bar local systems are always the same thing as continuous representations of this pro-étale fundamental group.
Okay, are there other questions? Okay, if not, let's thank Peter again. And we'll return in 15 minutes.
Need for petit camarade,
You mean the crystalline? Oh, yeah, okay. Yes, it's a coherent side.
So
But I don't know what the points
you
are.
don't know what the points are?
Um,
Among them, you must have the actual geometric points.
yes.
But then there's some other mysterious ones.
Yeah, so even in this case of an algebraically closed field, somewhere you have some kind of shrinking sets of profinite subsets of a profinite set.
So could you put one of those such points here?
I guess so. If you really want.
Why not? It's as good a point as any other.
Yeah.
Anything happens. If you're connected, you're just going to get the same thing every time. What is being sort of